problem 24, page 284. As you see in the figure, we have a bullet. Small m initially has a velocity v before the collision, and we have a pendulum of capital M initially at rest. The pendulum is attached to a stiff rod of length L and negligible mass. Okay, the bullet emerges with a speed of v over 2. It means here we have the bullet will go through the pendulum and emerges with a velocity equals to v over 2. Okay, emerges, it means I am talking the velocity is going out. Okay, emerges here, it means going out with a velocity equals to v over 2. we I told you in the last video, in this case we have directly inelastic collision because we have one object is passing through another object. In this case we have a friction inside the object. As we have friction, we have an increasing of temperature, we have internal energy, so we have inelastic collision. The question is, what is the minimum value of V such that the pendulum here, the pendulum will barely swing through a complete vertical circle? When I say barely, it means the pendulum will arrive to the top of the circle with about zero velocity. Okay, I mean at this point the pendulum has v equals to o, because if we have an object and I say I want to push the object in order to arrive barely at this point, it means the object will move to the right with a velocity will decrease, and at this point it will be zero. Okay, barely. Okay, let me open a new page. Here we have the example. We have the bullet before initially, let's say we have a collision just so I need to calculate V, the value of V, in order that the pendulum will arrive to the top of the circle at this point with zero velocity. Okay, here at this point we have collision, so we can apply, as we said, we have inelastic collision because we have one object passes through another object. We have inelastic. In this case, we can say P just before equals to P just after. So here P just before equals to P just after. This is about the collision at this point. Okay. What we have to do after the collision, we can take the pendulum between this point and this point, and we can apply the conservation of mechanical energy for the pendulum to calculate at this point. We can do the calculation. Anyway, let me start with this point. Before the collision, we have the pendulum and we have the bullet. Okay, here we have M and V, and the pendulum has capital M with V equals to O. We can say here we have V1 and here we have V2. Okay, before the collision, we have M V1 plus M times V equals to O. After the collision, we have the pendulum will start to move to the right with, we can say, with V2 prime. And the bullet here, after passing through the object, will continue to move with a velocity equals to V prime. We can say here V prime 1 equals to V1 over 2. Look here. The final velocity after the collision equals half the initial velocity. Okay, so if the initial one equals to V1, so the final one equals to V1 over 2. So finally we have M times V1 over 2 for the bullet plus M times V prime 2. Okay, here we have M1 times V1. I want to calculate V1. Okay, here we have V1 equals to M V1 over 2 plus M V prime 2. We have the value of M1 and M. To calculate V1, I need to calculate the value of V prime 2 of the pendulum. So I need to calculate V prime 2. Let me write before V1 the value of V1. M1 V1 minus M1 V1 over 2 equals to M V prime 2. So V1, we can say here 1 minus half. So we have half M1 V1 over 2 equals to M V prime 2. So we can write V1 equals to M1 times 2 V prime 2. So to calculate V1, I need to calculate V prime 2. Okay. So I need to calculate V prime 2. I can take the pendulum, only the pendulum, between this point. So now, as M1 and M, as the pendulum and the bullet are not connected, I can take only the pendulum. Okay, I'm talking about this. Just after the collision, we have the velocity here of the pendulum equals to V prime M. We can say V2 prime, and the pendulum moves to the maximum position at this point. Let's say here we have position A, and here we have position B. So I take between position A just after collision and position B when the pendulum reaches the maximum at this point. Okay. Here we have a conservation of mechanical energy. You know, in the case of isolated system, at any position we have a conservation of mechanical energy. So we can write ME initial, this is the initial position, equals to ME final. Initially, as you know, the lowest point, we can put the reference at this point. So initially, we have kinetic energy equals to M over 2 times V prime 2 square. We don't have potential, equals to O. Equals at the highest point, we don't have kinetic, but we have a potential equals to mgh. H equals to L plus L. Okay. So we get mg 2L. Here we can calculate, we can eliminate M and M. So V prime 2 equals to equals to 4GL. Okay, 4GL. This is the value of V prime 2. We substitute its value here to calculate V1. So we can write here V1 equals to M over M1 times 2 radical 4GL. Okay, we can do some simplification. Anyway, this is the value of V1 in order to have zero velocity at the maximum point. If we increase V1, so the velocity at this point will be increased. Here, the most important point, you have to know we have inelastic collision. Okay, I repeat because this bullet is going through the pendulum and emerges with another velocity. So here we have a friction, we have increasing of temperature, we have an internal energy, so we have inelastic collision. As we have inelastic collision, we can apply only the equations of inelastic collisions. We don't have a conservation of kinetic energy before and after the collision.